We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system.
We're looking at Neptune's orbit, and it's not following Newton's laws.
When Neil deGrasse Tyson unveiled his groundbreaking revelation about Neptune during a recent symposium, the astronomical community and the public alike were left in awe. Streamed globally to a packed auditorium, Tyson's articulate presentation shattered long-held assumptions about the ice giant, suggesting that Neptune is far more complex and dynamic than previously understood. This article delves into the details of his announcement, exploring the new findings, their implications for planetary science, and the broader questions they raise about our solar system and beyond. What follows is an expanded exploration of this revelation, weaving together the latest data, historical context, and the tantalizing possibilities that lie ahead. A historical perspective on Neptune. Neptune, the eighth planet from the Sun, has long been a distant enigma in our solar system. Discovered in 1846 through mathematical predictions based on irregularities in Uranus's orbit, Neptune was a triumph of celestial mechanics. Unlike planets identified through direct observation, Neptune's existence was inferred by the gravitational perturbations it caused, a feat credited to astronomers Urbain Le Verrier and Johann Galle. Since its discovery, Neptune has been studied through limited means, ground-based telescopes, the Hubble Space Telescope, and a single flyby by Voyager 2 in 1989. The Voyager 2 mission provided humanity's only close-up glimpse of Neptune, revealing a frigid world with a deep blue hue. Supersonic winds exceeding 1,300 miles per hour, and massive storms, including the now iconic Great Dark Spot. These observations painted Neptune as a dynamic ice giant composed primarily of hydrogen, helium, and methane, with a presumed interior of layered ices, a rocky core, and a gaseous envelope. Yet, the brevity of Voyager's visit left many questions unanswered, and Neptune remained a distant, mysterious orb on the fringes of our planetary family for decades. Astronomers relied on these snapshots and subsequent telescope data to construct models of Neptune's structure and behavior. These models described a planet with a differentiated interior, a rocky core surrounded by a mantle of water, ammonia, and methane ices, topped by a thick atmosphere. However, Tyson's recent disclosure, based on cutting-edge observations, suggests that this understanding is woefully incomplete, unveiling a Neptune that defies conventional planetary science. Tyson's revelation. New data, new questions. Tyson's announcement centered on a series of observations made possible by the James Webb Space Telescope JWST and Advanced Earth-based Interferometric Arrays. These instruments, with unprecedented sensitivity and resolution, detected anomalies in Neptune's internal composition, thermal output, and magnetic field that challenge existing models of gas and ice giants. According to Tyson, these findings reveal a planet far more volatile and complex than anticipated, with implications that ripple across planetary science. Anomalies in Neptune's interior. One of the most striking revelations is the discovery of irregularities in Neptune's internal structure. Traditional models assumed a smoothly differentiated interior, with layers organized by density, a rocky core, a mantle of icy water and ammonia, and a gaseous outer envelope dominated by hydrogen and helium. However, the new data suggest a far more chaotic interior, characterized by dynamic, churning movements that defy thermodynamic expectations for a planet so distant from the Sun. The JWST and ground-based arrays detected patterns in Neptune's gravitational field and thermal emissions that hint at a mosaic of interacting zones within the planet. These zones include intermittent regions of plasma-like materials and inexplicably warm patches buried beneath the cloud tops. Such warm regions are particularly puzzling, as solar energy at Neptune's distance 30 times farther from the Sun than Earth is too weak to account for them. Unlike Jupiter, which generates significant internal heat from gravitational compression, or tidally heated moons like Io, Neptune lacks an obvious external heat source. Tyson posited that an internal process, possibly involving exotic chemical or phase transitions, is generating this unexpected heat, a shifting magnetic field. Neptune's magnetic field, already known to be unusually tilted and offset from its rotational axis, appears even more enigmatic in light of the new data. Observations indicate that the field is not static, but in flux, with sections drifting and reforming in cyclical patterns not previously documented. This erratic behavior suggests that Neptune's internal dynamo, the mechanism generating its magnetic field, may operate differently from those of other planets. In most planets, magnetic fields are generated by the convection of electrically conductive materials, such as metallic hydrogen in Jupiter or molten iron in Earth's core. For Neptune, scientists hypothesized a dynamo driven by a layer of conducting ices or fluids under high pressure. However, the new data point to a shell of exotic ices undergoing chemical transformations, producing charged flows that create a shifting magnetic map. Tyson raised the provocative possibility that Neptune's interior contains stratified cavities, or pockets that act as resonant chambers for electromagnetic and gravitational energy. While speculative, this idea suggests a fundamentally different internal architecture, challenging the notion of planets as uniformly compressed spheres. Exotic materials and superyonic ice. Adding to the intrigue, Tyson highlighted evidence that Neptune's atmosphere and interior may host superyonic ices, materials that exist in a strange state between solid and liquid. In superyonic ices, water molecules lose their hydrogen atoms under extreme pressure, forming a slushy, electrified medium that conducts electricity. These ices could explain some of Neptune's heat generation and electromagnetic anomalies, as they may move in vast conveyor belts beneath the surface, creating currents and turbulence unlike anything observed on Earth or other gas giants. The presence of superyonic ices, previously confined to laboratory simulations, suggests that Neptune's composition is far more exotic than previously thought. These materials could form a significant portion of the planet's structure, influencing its thermal, magnetic, and atmospheric dynamics. The discovery of such phases of matter in a natural setting could revolutionize our understanding of planetary interiors and the behavior of matter under extreme conditions. Irregular radio emissions. Another startling finding is the detection of irregular radio emissions from Neptune's atmosphere. While the planet is known to emit radio waves due to interactions between its magnetic field and the solar wind, these new emissions originate deeper within the planet and exhibit frequencies inconsistent with atmospheric activity alone. Some researchers speculate that these signals point to quantum-level behaviors or unrecognized chemical processes occurring in Neptune's dense interior. These emissions add another layer of mystery, suggesting that Neptune may host phenomena not previously observed in our solar system. Internal drivers of extreme weather. Neptune's atmosphere is known for its extreme winds, which reach speeds exceeding 1,300 miles per hour, faster than any other planet in the solar system. Traditional models attributed these winds to differential heating and rotational dynamics, similar to processes on Jupiter. However, Tyson's presentation suggested that internal thermal pulses, possibly driven by phase transitions or instabilities in the planet's exotic materials, could be the primary drivers of these winds. If confirmed, this would mark Neptune as the first known planet whose weather is predominantly fueled by internal dynamics rather than external solar energy. Implications for planetary science. Tyson's revelation has far-reaching implications, not only for our understanding of Neptune, but for planetary science as a whole. If Neptune's internal structure and behavior deviates so radically from current models, it forces a re-evaluation of the formation and evolution of our solar system. Revisiting solar system formation. Neptune is believed to have migrated from a closer orbit to its current position during the early solar system, a process that shaped the Kuiper belt and influenced the orbits of other planets. Some theories even suggest that Neptune's gravitational interactions contributed to the ejection of a hypothetical fifth giant planet. If Neptune is a more chaotic or exotic entity than previously assumed, the story of our solar system's adolescence becomes far more complex. The planet's unusual internal dynamics could indicate a more turbulent formation history, with implications for the distribution of material and the stability of planetary orbits. Exoplanet research findings also have significant implications for exoplanet research. Neptune-sized planets, often called mini-Neptunes or sub-Neptunes, are among the most common types of exoplanets detected by missions like Kepler and TESS. If Neptune itself is fundamentally different from our assumptions, then the models used to classify and understand these exoplanets may need revision. Tyson emphasized that our assumptions about composition, habitability, and evolution could be off base, potentially affecting the search for life on similar worlds. A new category of celestial bodies. Perhaps the most provocative idea raised by Tyson is that Neptune may not fit neatly into existing categories of planets or brown dwarfs. Its internal heat, dynamic energy systems, and possible cavities suggest it could represent a transitional class of celestial bodies, neither fully a planet nor a failed star. This challenges the binary classifications that have dominated astronomy and suggests a greater diversity of planetary architectures than previously considered. Neptune's chaotic system in equilibrium, as Tyson described it, points to a body driven by self-balancing forces in constant flux, a concept that could redefine how we view planetary evolution. The role of advanced technologies and underscored the critical role of advanced observational tools in uncovering these findings. The JWST's ability to capture high-resolution infrared data, combined with the precision of Earth-based interferometric arrays, revealed signals that would have remained hidden with older technology. These instruments allowed astronomers to probe Neptune's gravitational field, thermal emissions, and magnetic behavior in unprecedented detail. Tyson's presentation served as a reminder that our understanding of the universe is tied to the tools we build, and as our observational capabilities improve, so too does our ability to uncover cosmic surprises. Broader implications and future directions ripple effects of Tyson's revelation extend beyond Neptune itself. If one of our own planets can surprise us so dramatically, it raises questions about what else we may have overlooked in our solar system and beyond. Neptune, once considered the quieter, colder cousin of the inner gas giants, has emerged as a dynamic and exotic world that challenges our assumptions about planetary behavior. Scientific humility and the thrill of discovery. Tyson's announcement is a testament to the humility of science and the unpredictability of discovery. It reminds us that even well-studied objects can harbor secrets that upend our understanding. The revelation invites astronomers to revisit fundamental questions about planetary formation, composition, and dynamics, while inspiring the public to engage with the mysteries of the cosmos. Future missions to Neptune findings have sparked renewed interest in a dedicated mission to Neptune, which has not been visited since Voyager 2's fleeting encounter in 1989. A future orbiter or probe could provide detailed measurements of the planet's interior, magnetic field, and atmosphere, helping to confirm or refute the hypotheses raised by Tyson's announcement. Such a mission could also explore Neptune's moons, particularly Triton, which may hold clues to the planet's formation and migration history. Public engagement and inspiration. Tyson's ability to communicate complex scientific ideas to a broad audience has amplified the impact of this discovery. His call to smash the like and subscribe buttons during the symposium was a playful nod to engaging the public in science, encouraging curiosity and discussion. The global reaction to his announcement evident in comments and posts on platforms like X demonstrates the power of science communication to inspire wonder and debate. Conclusion Neil deGrasse Tyson's revelation about Neptune has thrust the ice giant into the spotlight, revealing a world that is far more complex, dynamic, and exotic than previously imagined. From its chaotic interior and shifting magnetic field to its supersonic ices and internal weather drivers, Neptune challenges our understanding of planetary science and invites us to rethink the architecture of our solar system. The implications extend to exoplanet research, celestial classification, and the very tools we use to explore the cosmos. As we stand on the brink of a new era of discovery, Neptune reminds us that the universe is full of surprises waiting to be uncovered by those bold enough to look. What are your thoughts on this revelation? Could Neptune's anomalies reshape our understanding of the solar system? Share your ideas and stay tuned for more cosmic updates as we continue to unravel the mysteries of the ice giant.